A very, very good afternoon. A very, very good afternoon to you, ladies and gentlemen. Very good afternoon to you, especially dear children. I am holding in my hand here one of the most extraordinary substances known to the human race. It's called sulfur. Sulfur has been known ever since the dawn of humanity, since the oldest times, going back tens of thousands of years ago. And it was found in volcanic regions, and that's where people were used to conglomerate, etc. And one of the most remarkable things they found about this yellow solid here, which they didn't have a name for in those days, is that it burns. So I'm going to start off with my first experiment and show you just how this burns, how sulfur burns. And then I will explain to you how its name has changed throughout history. So here we have a small sample of sulfur. I'm going to obviously be using modern technique to set it on fire. That's with a blowtorch like this. So please excuse me while I open up the flow of gas. So there we are. And, oops, just press it into place. So please watch carefully now as I'm setting this stone on fire. Could we have the lights off, please? And there you see, it's burning. It's burning with a blue flame, which is quite almost invisible, but giving off the most foul and acrid fumes. And because of that, I'm going to put the flame out immediately. So if you excuse me, I'm just going to squirt some water on it. So there is our burning stone, which in Old English was called brimstone. In fact, it was called Brimstan. In Old German, it was called Brennstein, the burning stone. We've extinguished the burning stone now, and some of you may, in a short space of time, be able to detect a most unpleasant smell. And that's one of the things that's associated with sulfur and with its compounds is unpleasant smells. So if by the end of today's talk you haven't experienced a bit of an unpleasant smell, you'll have missed the entire point of the talk in many ways. So there we have sulfur then, burning stone. In Old English, as I said, brimstan. In modern, in slightly more recent English, brimstone. The word is still used today. And it, as you see, it burns there. Having showed you that, and I wanted to tell you that it's very frequently found in volcanic regions. So if we can have the first, there you have a slide. This is a volcano in Guatemala. There are about 50 active volcanoes in the world at present, and Guatemala is in Central America, just south of Mexico, and there are several volcanoes there indeed. And if you look at that cloud of smoke, that is a smoke full of sulfurous fumes, of the sort of smell that some of you might be able to detect at the moment. Sulfur comes out of the ground, from deep under the ground in the Earth's interior, and for that reason, it has been associated with all sorts of evil things deep down under the ground. I am now going to turn to to tell you that in our language we call it sulfur, but the word sulfur has a very interesting origin. It actually, the origin of the word goes right back to one of the most ancient civilizations, the Hindu civilization, the Hindu religion of the Indian people, dating back over 5,000 years ago. They had a word for sulfur, which was actually in the oldest language of the world, which is Sanskrit. And their word was sulvari. Now, sulvari in Sanskrit means the enemy of copper. And I have actually photographed the reaction, especially to show you how sulfur, in fact, destroys copper and why they would have called it the enemy of copper. So you see, in my boiling tube there, I have a Bunsen burner, and there is some yellow sulfur at the bottom, and there is some beautiful shiny copper foil. And as the reaction proceeds, can we have the next slide, please? Thank you very much. You see it's glowing red hot. Now, that is the process of destruction of the copper by the hot sulfur vapors. And at the end, this is what the copper turns to. At the top, you see, we have this black solid. It started off as copper on the bottom, and it's ended up as the black solid on the top. Now, in today's language, we call that copper sulfide, but in the language and the experience of ancient people, this was actually demonstrating the destruction of copper. Copper is a beautiful, shiny metal, but once it had reacted with sulfur, it turns to a black, crumbly solid. And that's where we derive our Latin. The Latin, incidentally, becomes sulfur, and that today, as in the modern English, we call it sulfur. Let us now turn to a short investigation of these acrid fumes. I'm going to burn some more sulfur for you now. Andres, could I please ask you to put on the burner now, Andres is one of my several assistants today, and I will be introducing them one at a time. And I'm going to, while Andres is getting the burner going, I'm going to tell you what I'm going to do. I'm going to take a few pieces of sulfur, which I have here is this beautiful solid. Thank you very much. And I shall be setting fire to them in my deflagrating spoon. This type of spoon, which we have here, is used especially for burning substances in special containers which are called gas jars. So Andres is holding the gas jar there, you see, and I'm going to set this sulfur on fire. You will barely see the flame, but then I'll ask for the light to be turned off once the sulfur has gone in. So there is no rush, by the way. It does take a little while. Initially, the sulfur will melt. Initially, it's melting. There you see it's got that orange color there. I'm going to make it burn in a second. You'll see fumes coming off from it. You'll see sulfurous fumes. There it's dripping. And now, lights off, please. Thank you very much. And there you see sulfur beautifully burning in a gas jar full of oxygen. And there we can turn this burner off now. And that you see is the typical color of sulfur burning in oxygen. It is a blue flame, and you can see the fumes coming off. And those fumes are the same fumes which I produced right at the very beginning. And whenever you burn sulfur, this is what you get. But today, we're going to just investigate this in a little more modern scientific way. Now, the sulfur is continuing to burn there. So I am now going to very carefully put a lid, because I don't want to smell this, and put the sulfur into some cold water. You saw it go out immediately, and the flame has now been extinguished, so we can put our spoon down there. And we now have a jar full of sulfurous fumes, dear children. What I'm now going to do is show you what happens when we allow water to mix with these sulfurous fumes. I have here a special trough, which has got water in, and it's been colored green, by the way. The water has been colored green with a special indicator called universal indicator. I now push off, and look what's happening inside. As if by magic, the water has gone up inside. It started off red, and now it's gone yellow. And you see, dear children, what that has shown us? It has shown us that the sulfur dioxide, the gas is called sulfur dioxide, I can tell you now, these acrid fumes, and it is actually quite acidic. I'm just going to, if you excuse me, I'll be regularly dipping into my supply of goodies, which is under there. So I'm just going to clean my hands off. So this sulfur dioxide, you see, is the acrid substance which is formed, a weak acid in today's world. We call, by the way, the sulfur dioxide is the gas, but when it reacts with water, it makes sulfurous acid. So all of this adds up to the fact that so far I've showed you the unpleasant side of sulfur. I've showed you that it emits horrible, smelly fumes, which some of you might have already noticed. It produces a gas, sulfur dioxide, which is acidic and which dissolves in water, which is also bad for us. And furthermore, it comes out of the ground, out of volcanoes. Now, in various parts of human history, things that come deep from underground have had very very evil connotations. That's associated in ancient times with things being dark and dangerous and unpleasant and evil. And during the rise of various religions and in various ancient cultures, that it was associated, sulfur was associated with evil. And especially so in Christianity. About over 2,000 years ago, for the Christians, sulfur had a particularly unpleasant connotation. It had connotations of hell, damnation, doing things bad, and people going down deep into the dark underworld if they as a punishment for their sins. So it had a whole lot of unpleasant connotations, which we today, of course, know are not true, but that's we are humans and we think about these things. And these unpleasant connotations sparked off a huge amount of literature. A huge amount of people wrote about the evilness of sulfur. They used the evil aspects of sulfur in various works of literature, in painting, in sculptures. And I would just like to present for you just three extracts from three pieces of very, very well-known literature, which many of you will have heard of, and I will briefly tell you what they are. The first extract which you will hear is a very short piece from John Milton's epic poem called Paradise Lost. Now, John Milton lived about 400 years ago, and he was involved in Oliver Cromwell. He was Oliver Cromwell's secretary. He lived at the time of King Charles, and he was so there was the fight between the Cromwell and the Royalists, and he saw the very bad side of humanity. There were all sorts of issues, and he wrote an epic poem called Paradise Lost, which was a sort of a biblical look of the summary of man's descent into eternal damnation. That will be the first piece which you'll hear. The second piece will be a quote. Just William Shakespeare used the word sulfur as well in his quotations, and there will be a very short quote from the very well-known play Othello, in which Othello accidentally, he misunderstood everything. He killed his wife, and he was so upset by this that he then uttered a few words which you shall see before he killed himself in utter despair at having killed his own beloved wife. And finally, there is a special fragment of a special story, especially for children, and it concerns some very, very naughty and nasty school teachers. And I'll tell you, dear children, it is a piece of a poem, in fact, of a story by Charles Dickens, the brilliant author. And Charles Dickens wrote a book called Nicholas Nickleby, which some of you will have read, I hope. Nicholas Nickleby, and in this particular passage which you're going to hear, Nicholas was wanting to become a school teacher. He was a young teacher, and he was training to become a teacher, and he went to a boarding school to do his training, where he came across a very, very nasty headmaster called Mr. Squeers. Now, Mr. Squeers had a very unpleasant and nasty wife. She was called Mrs. Squeers. And together, they tried to make money off the poor children. And do you know how they did it, children? It was quite horrendous. They used to, you see, the children were in a boarding school, and they all came from poor families. And what they did, these horrendous teachers, Mr. Squeers and his wife, Mrs. Squeers, they tried to make money off the children by not feeding them properly, by saving money on food. And do you know how they did it? They fed them they gave them a very unpleasant medicine, which involved brimstone, which is the old name for sulfur. And the purpose of giving them that medicine, as they explained, is that the children would feel so ill and so sick that they wouldn't want to eat anything. And there, Mr. Squeers said, we can save money because we don't have to buy any food. Now, isn't that terrible? Now, I have asked my good friend, Mr. Stephen Lucas, a professional actor, who will read you those 3 passages for you, and I very much hope you enjoy them. You will first hear John Milton, then you will hear William Shakespeare, and then you will hear Charles Dickens. And for the Charles Dickens, the slide will come up just before the Charles Dickens. So thank you very much, sir. I hand over. John Milton.
Turning our tortures into horrid arms against the torturer, when to meet the noise of his almighty engine, he shall hear infernal thunder, and for lightning see black fire, and horror shot with equal rage among his angels, and his throne itself mixed with Tartarian sulfur and strange fire, his own invented torments. But perhaps the way seems difficult and steep to scale with upright wing against a higher foe. From Othello, William Shakespeare. Oh, cursed slave! Whip me, ye devils, from the possession of this heavenly sight. Blow me about in winds, roast me in sulfur, wash me in steep down gulfs of liquid fire. Oh, Desdemona, Desdemona, dead! No. Oh. And finally, from Nicholas Nickleby by Charles Dickens. Come in, my dear, said Squeers. And Mrs. Squeers came in, still habited in the primitive night jacket which had displayed the symmetry of her figure on the previous night, and further ornamented with a beaver bonnet of some antiquity, which she wore with much ease and lightness upon the top of the nightcap before mentioned. Drat the things, said the lady, opening the cupboard. I can't find the school spoon anywhere. Never mind it, my dear, observed Squeers in a soothing manner. It's of no consequence. No consequence? Why, how you talk, retorted Mrs. Squeers sharply. Isn't it brimstone morning? I forgot, my dear, rejoined Squeers. Yes, it certainly is. We purify the boys' bloods now and then, Nickleby. Purify fiddlesticks' ends, said his lady. Don't think, young man, that we go to the expense of flour of brimstone and molasses just to purify them, because if you think we carry on the business in that way, you'll find yourself mistaken, and so I tell you plainly. My dear, said Squeers, frowning. Oh, nonsense, rejoined Mrs. Squeers. If the young man comes to be a teacher here, let him understand at once that we don't want any foolery about the boys. They have the brimstone and treacle, partly because if they hadn't had something or other in the way of medicine, they'd always be ailing and giving a world of trouble, and partly because it spoils their appetites and comes cheaper than breakfast and dinner. So it does them good and us good at the same time, and that's fair enough, I'm sure.
Thank you very much, sir. Thank you very much, sir. Well, thank you very much. Absolutely brilliant. Thank you so much indeed. Thank you. So there you see, dear children, you've seen the evil side of sulfur. Horrendous indeed. I am now going to tell you some good things about sulfur, some slightly different things. And people have always wondered ultimately what things are made of. They've wanted to enjoy and use things that are found in the ground, in the air, in water, and all around them. And one of the interesting things that they started finding when in ancient times as well is these nuggets like this, you see. Now, what I'm holding here used to be called fool's gold. You see, they look quite golden, and people used to believe in a simple manner that this is actually a kind of a gold. But of course, it was called fool's gold because we know it's not real gold, and only a fool would believe it and then try and make money of it. However, people, because they were always curious, all humans are interested in to know about the world and to exploit the wonderful things that we have in the world. They have always explored. And one of the things, yes, Andres will now set the burner on fire, so thank you very much indeed. And I wanted to show you what's going to happen when we heat fool's gold. It's certainly not going to make gold. It's not going to melt into liquid gold. We've got the burner under there, thank you very much. And I want you to observe carefully what's going to happen inside that tube. There are some crushed pyrites. By the way, the name is pyrites today, and I've aimed them away, and I've aimed the tube away from the audience because there might be a little bit of crackling and a little bit of noise, but the pyrites are being heated. And I want you to listen carefully. I'm going to just adjust the flame a little bit and listen and watch carefully to see whether you could see any gold coming out. Just going to lower it a tiny bit. Just lower it a tiny bit. Takes a couple of minutes, this experiment. Just lower. So we're keeping our fingers crossed. And there's maybe a second burner. Let's just have another burner on. Let's play a second burner. Sorry, we want to get things going. It will happen, but we have to improvise. Thank you so much. Thank you very much, sir. Ah, did you hear that? Yeah, whoops-a-daisy. That's okay. Part of the fun. Hey, Realm. That's more fun. It looks fun, but it's not doing the job. As you can see, I don't do this regularly. We normally, in school, we have I'll just have to give this one up. Sorry about that. But I think you could see what's happening. And this is the important thing. This is the important thing. It's now beginning. I want you to look here, dear children. And you can see the appearance of this yellow color. And you could also, I'm sure you did hear a little bit of crackling. Ah, did you hear that? You see, now that has a very special name. That crackling has a very special name, and in the world of chemistry, we call it decrepitation. What that means is that it's a mechanical thing. You see the crystals, they were large lumps in there. They're breaking up into a powder now. Now, the reason why that happens is because when you heat things up, did you see that? Yes, it shot something out. And the reason is that when you heat things up, they expand on the outside, but not on the inside. It's a thermal effect, and this pyrites are very brittle, and as they break up, making this loud crackling sound, and indeed shooting out a few bits out through our long tube here, at the same time, so there's a physical change going on, that's the breaking up, but from our point of view, the interesting thing is the yellow stuff which you see here. Now, not only can you see the yellow solid which is now beginning to collect here, I'm sure you all know what that is. It is sulfur, dear children. We're actually getting sulfur out of these pyrites. And can you see that beautiful dark brown vapor in there? That is nothing other than sulfur vapor. It's the actual element itself, this yellow solid which I showed you earlier, it's actually coming off in the form of a vapor. And on the cooler part of the tube, it is actually condensing to form a liquid lower down, an orange liquid there, and a yellow liquid higher up. Now, I think the demonstration has been very successful, and I can just show you, just take this up now. Excuse me, I'm just going to take it out, so that, hold it up for you. Thank you very much, Andres. Thank you very much. So we can all very quickly just have a look once again. So what we have here, you see, is the broken up pyrites. At the same time, they have chemically changed. They've released some sulfur, and that you could see, which is condensed there. And at the same time, they have changed themselves. They have changed themselves into another kind of iron sulfide, but I'm not going to go into the details of that at the moment. I'm going to tell you a little bit more about other minerals in the Earth's crust which contain sulfur. You see, pyrites is the most widely distributed mineral of sulfur, which the chemical name is iron sulfide. It's a kind of iron sulfide. It has a formula FeS2. And already thousands of years ago, people had recognized that when you heat it, you actually make sulfur, which I just showed you. And I wanted just to show you a few other samples of these pyrites known as fool's gold. This beautiful mineral specimen here has been lent to us by the Geological Society of London, which is very close to here, and wonderful people. They have specially lent this, and you see, as I move it around, you can see the glittering of the pyrites, which are, this is called an encrustation. They are encrusted into this piece of rock here. But not only does sulfur appear, dear children, in iron sulfide, because this is the most widely distributed metal in the Earth's crust, that are compounds of iron, but it also appears in combination with other metals. And I just wanted to show you, I have in my special box here, which you'll all be able to have a look at afterwards and come and see it close up. This, you see, this mineral here, this is called galena. It's lead sulfide. So it's got another metal associated with it, the metal being lead. Beautiful silver crystals. If you heat this strongly, this too will make sulfur come off. And then we've got one other mineral. There are many other sulfides, but this one is a particularly special one, known in the ancient world as dragon's blood. And the reason is it has this red color. But dear children, when they heated this strongly, this was particularly well known in ancient China and also in southern Spain. This particular mineral, which has this dark red color, when you heat this mineral strongly, it makes two very, very remarkable substances. One of them is sulfur, which I'm holding for you in this special bottle here. You can see there's sulfur, I've shown you, but the other substance it makes, quite remarkable, is the liquid metal, which we call mercury. And this metal has a very high density. You'll be able to experience this yourselves. So when you heat that mineral very strongly, it breaks up into these, mercury and sulfur. Now, this fired up the imagination of the ancient philosophers, because they were asking questions about ultimately, what are all metals made of? They wanted to find out. They saw that metals all could be nicely bent. They knew that metals had a beautiful luster to them. And they wanted to find out, ultimately, how they were constructed. They came out of the Earth's ground. And a most interesting theory was devised. Approximately, this would have been 2,000 years, not quite 2,000 years ago, but it was initially derived by the great Arabic alchemists in the 8th century, something like that, 8th or 9th century AD, and they came up with the idea that ultimately all metals are composed of sulfur and mercury, of these two. Mercury had a very special significance in the ancient world because mercury is the only metal which is a liquid. Furthermore, it has a very high density. When you come and pick up this bottle, woof, this is seriously heavy, dear children. And they found out, they therefore assumed that these two are the main ingredients and the only ingredients of all metals. Now, this was called the sulfur-mercury theory. And their reasoning was very straightforward. They said, look, if you mix this with this in the right proportions, you can make any metal. You see, I have a gold ring on my finger. Gold was always renowned as the most perfect metal. It never corroded. It had wonderful properties of shining, etc. So they said that, look, this is, add a bit of this to that, and you get this, you see. Here's a beautiful piece of copper pipe, you see, nice and shiny. And you say, add this, a bit more of this to that, and you'll end up with this, you see. Now, to us today, you say, well, that, you know, we know that doesn't work, and you smite it with those people, that can't be right. Dear children, science is very difficult. And in the ancient world, people used to have a different way of looking at the universe. It was what we call a world of correspondences. That means if something looks like something, then it could well be that it is actually made of things that make it look like something. And that way of thinking, which today say, oh, well, that's pretty stupid. No. That was the cleverest way. That was the way people used to view the world in those days. And this sulfur-mercury theory was so amazing that people continued to use those two substances to believe in them for 1,000 years. And there we have a beautiful demonstration here from a book published in 1614 of the sulfur-mercury theory. There on the right-hand side there was a book especially written about 12 of the greatest philosophers of all time. On the right-hand side is Thomas Aquinas, who was a great theologian, a Catholic theologian, and he's pointing to a sort of a diagram of a volcano. And on the left-hand side, you see symbols, those alchemical symbols for mercury and sulfur, which are actually being heated up in the earth. And as the vapors go up, they come to the model volcano. There is the alchemist standing on top, and he is mixing or combining them to make any metal. Dear children, how extraordinary is the human imagination. We humans are all curious. We want to know how the world works. Today, we live in a world where we take the achievements of science and technology for granted. We think we are clever. Of course we are. But what you must understand is, no matter how odd or erroneous you might think the ancient theories were, they were being made by people at least as intelligent as we are today. And which is on the basis of those theories that we have the world that we live in today. Who knows? In 1,000 years' time, people may be looking back on the theories of today and they will have made considerable advances. That is the nature of progress, my dear friends. So the sulfur-mercury theory was so impressive for so many people that many philosophers wrote about it. And I wanted just to ask my friend Stephen to read from you 2 more passages, because many people wrote about the sulfur-mercury theory. The first passage will be from the English alchemist and natural philosopher Roger Bacon, who lived in the 13th century, but the work was published in the 16th century, possibly not his original writing, but nevertheless, you will see what he had to say about the sulfur-mercury theory. And then we will have 2 readings from the Polish alchemist Michael Sendivogius, who is the only person who devoted an entire book just to sulfur. So please, first of all, Roger Bacon, sir.
The natural principles in the mines are mercury and sulfur. All metals and minerals, whereof there be sundry and diverse kinds, are begotten of these 2. But I must tell you that nature always intendeth and striveth to the perfection of gold. But many accidents coming between change the metals. For according to the purity and impurity of the 2 aforesaid principles, mercury and sulfur, pure and impure metals are engendered. Sulfur is not the last amongst the principles, because it is a part of the metal, yea, and the principal part of the philosopher's stone. And many wise men have left in writing diverse and very true things of sulfur, For the blood of sulfur is that inward virtue and dryness which congeals quicksilver into gold and imparts health and perfection in all bodies.
Thank you very much. So there you see Sendivogius on sulfur. One more. Now, there you see the philosophy. That's the philosophy, that's the sulfur-mercury theory. But Sendivogius then, he went on to see sulfur's role in a far greater way. In his book on sulfur, close towards the end, he expressed what he thought about sulfur and its contribution to our existence on Earth. So please, sir, the final text now from Sendivogius.
He can perform 1,000 things and is the heart of all. He can perfect metals and minerals, impart understanding to animals, produce flowers in herbs and trees, corrupt and perfect air. In short, he produces all the odors and paints all the colors of the world. Know, friend, that sulfur is the virtue of the world. And though nature's second-born, yet the oldest of all things.
Thank you very much, sir. So there you see, we have had two different pictures of sulfur presented. We have sulfur presented as related to evil, and now as sulfur, the ultimate perfection. So dear children and dear friends, I'm going to continue now on the good side of sulfur, because that is really what the purpose of this talk is to extol on the wonderful properties of sulfur. And I believe that the next topic I have to talk about is sulfuric acid. Is that right? The oil of vitriol. So I wanted to tell you that I have some beautiful crystals here, and I wanted to tell you that these crystals had already been observed, these green ones and the blue ones, which you'll see down there, they had been observed on the side of lakes, of water evaporating on the side of lakes where close to volcanoes, and they had a sort of a glassy appearance. Now, the first peoples who actually observed these were the Sumerians 2,000 years ago, and they noted it and they described these crystals. The Latin word for glass is vitriolus, and so glassy substance became known as vitriols. And it is on the subject of vitriol that I wanted to talk a little bit, you see. And to start off with, they found out already, the medieval chemist discovered that if you heat these very strongly, these crystals, they give off a sort of a terribly powerful smell, and they make a liquid which is capable of dissolving other metals. Now, that liquid today, we call it oil of vitriol. It was called oil of vitriol because it came from those glassy substances, but today we call it sulfuric acid. So I'm now going to tell you a little bit about sulfuric acid, about the remarkable properties of this acid, and to show you how it can dissolve metals, because this is one of the things that people found particularly remarkable, is to find a substance that could dissolve metal. So everything you see metallic around you, something that can dissolve it. Well, this is the oil of vitriol, otherwise known as sulfuric acid. And I'm going to talk about this topic in three different contexts. One is to show you its reaction with zinc, which I have already put in this flask here. Another, and that's dilute sulfuric acid. We will then turn to some experiments with concentrated sulfuric acid. And finally, I shall tell you a little bit about the uses of this most extraordinary substance, sulfuric acid. There are few things that we use today which are not related to sulfuric acid or to sulfur. Please allow me. I'm going to now, in this flask here, I have zinc, some zinc turnings, which is a metal, and I have some copper sulfate acting as a catalyst. Whoops-a-daisy, that's not necessary there. I'm just pouring in because I'm getting the reaction going. That's of no trouble at all. I'm just pouring in a little bit of sulfuric acid here, and you will shortly see bubbles coming out. In fact, you could see them already coming out. Now, the reason why the bubbles are coming out is because the zinc is reacting with the sulfuric acid to make a gas. The gas is what we're seeing. But today, we're going to be interested not only in the gas, but what gets left behind in the reaction there, and what the zinc has turned into. So you see the gas bubbles are now rising, dear children. So we will now put our gas jar over very carefully. There is our gas jar, and you see the bubbles are going in. Now, these are bubbles of a gas, which is the lightest gas in the universe. It's called hydrogen. And that gas is related to all acids, because all acids contain hydrogen ions, as we have discovered, and they release this gas when they react with metals, and they dissolve the metals. So I'm now going to just adding a little bit more acid, just to speed up the reaction a little bit for you there. And as it speeds up, I shall collect the jars. I shall collect the jar of the hydrogen, and we do this by placing a lid underneath, and then we'll put another jar like this. This technique, by the way, for collecting gases was developed by the great English chemist Joseph Priestley. This was towards the end of the 18th century. That's when pneumatic chemistry, or the chemistry of gases, made huge advances. Dear children, while that's bubbling away, thank you very much, Andres. Thank you so much. I'm just going to show you how this jar burns. Andres, could you please hold this while I set fire to it? And this is hydrogen burning. There we are. Yep, let's go. And you see, that's hydrogen. Now this one, Andres, let's do this one here quickly. We're mixing this with air. This one's mixed with air. Just listen to this. It should make a slightly different sound. And you see, that's the difference, you see. And when you mix it with air, there's a little explosion. Thank you very much. Now let me tell you, dear children, the important point, we'll just leave that there. I think that's wonderful on its own there. Thank you very much. I wanted to tell you that the types of substances which are made when metals dissolve in acids, they're called sulfates. That's the way we call it today. In the olden language, they were called vitriols. And I just wanted to show you a few examples. So here I have some beautiful crystals of copper sulfate. You see, that used to be called blue vitriol. So by dissolving copper, today we dissolve copper oxide in sulfuric acid, we make blue vitriol. Here we have some examples of iron sulfate, which is iron vitriol, which is the first sulfate substances that they made the acids from, you see, that they made the sulfuric acid from. And in this little tray here, I have some crystals of white vitriol. Now, it hasn't fully crystallized because I prepared this experiment for you a few days ago. I allowed that reaction to go overnight, and I poured the solution into here, and there are crystals appearing. Now, we call it, today we could say it's white vitriol. That was the old language, but it's actually called zinc sulfate. So that's the name. I've made some zinc sulfate, and hopefully by the end of the lecture, they may have also turned into a little more crystalline solid. But I did want to show you a most interesting mineral, my dear friends, and something that I find personally extremely beautiful. And this is also a sulfate. This comes out of the ground, dear children. And do you know, almost every one of you will have lots of this in your houses. Lots of this in your houses. Now, where on earth will you have this? I'll tell you what it's chemical. I'll tell you first of all the name for it. The mineral is called gypsum. The chemical name is calcium sulfate. And what do we make from calcium sulfate? We make plaster. So if you have a room with plaster on the walls or plaster on the ceilings, this is what it is made of. A remarkable use, you see, of this splendid type of substance, sulfate. Once again, sulfur playing a key role in our everyday lives. And dear children, not only that, we have wonderful uses of sulfuric acid on an everyday basis. And for instance, did you know that just about every single motor car which you have has sulfuric acid in it? That's the cars which either run on diesel or on petrol, of which there are many on the road. And do you know where the sulfuric acid is, dear children? It's inside the car battery. Now, I have asked Jacob to come and help today. Jacob is a student from Sheffield University, and he's a chemistry student, and he expressed an interest when I visited Sheffield University for the chemistry talk which I gave. A wonderful young man. So Jacob is going to just show you very simply how we can use the electricity from a battery, a car battery, which is made of lead, essentially two lead electrodes, but one of them is actually lead oxide inside, and it's full of sulfuric acid. So please, maybe some help, just fire away. This is something that you all have in your car. See if you can recognize it. There we are. Beep, beep. Let's make a few beep, beep sounds on it, because I like hearing sounds. Beep, 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 beep. Let's have some melody. Oh, dear. Never mind. There we are. Jacob, thank you so much. There we are. And now something else. Let's have a light. I'm just going to hold this. You carry on. Fire it up. I want to shine a beam at everyone there. And there we are. Can you see that, dear children? There you are. A headlight, a car headlamp. And there we go. And this is all powered by sulfuric acid. Jacob, thank you so much indeed. So there we are. That's a little bit on sulfuric acid. I am now going to talk a little bit about concentrated sulfuric acid. Now, for this purpose, I have invited my good friend, Professor Fabio Parmigiani, who has especially come from Italy for today's talk. So over to you, dear sir.
Thank you very much. Thanks a lot.
Yeah.
So I have here a very special sample of sulfuric acid. Actually, it's in a bottle with an engraved label. So that's quite an ancient type of bottle that's no longer in use in chemical laboratories. It's engraved in Italian. It says acido solforico concentrato, which is obviously, as you can guess, concentrated sulfuric acid, which is a completely different thing from what Andrew showed before. That was about 20-25%, I think, more or less. This is 98%, so we need to treat it with a lot more care and a lot more respect. This is also something quite dear to me because it comes from the very same department where the one and only Nobel Prize of Chemistry that we had in Italy up to now worked for many years. He was Professor Giulio Natta, and this comes from could be his laboratory. I don't know if he ever physically handled this bottle, but it comes from that laboratory. And it's nice because it's engraved, so even if some of the concentrated liquid spills over, the label will not be destroyed. So that's quite beautiful. So we're going to show you just 3 experiments using sulfuric acid, and the first one will be, it's quite difficult actually, we'll try to make this happen for you. It's to write on a little bit of paper. So I have here a piece of tissue paper, and we'll try to write it, to use it as an ink to write on paper. This is supposed to be a representation of what happens when you would spill some of that on your skin. I mean, paper is made of cellulose. Our skin is not made of cellulose, but it's kind of a living material. So we'll need to pull this paper very carefully. I have here a teat pipette with which I will withdraw a little bit of the acid. It's a very viscous liquid, so it takes a while to fill the pipette properly. But I will try to write something for you with this. I don't know if you can see that, but the paper is instantly turning brown, and it's going over very slowly, because if you spill it too quickly, it will go all over the place. But I'm trying to write something for you. I don't know if you can make out what I'm trying to write. It's H2SO4, which is the formula for sulfuric acid in modern days. So you notice that the paper is turning almost black, I would say dark brown, possibly black, and in a few minutes it will be completely destroyed, because this is a very corrosive liquid, not only because it's a corrosive acid, many acids are corrosive, but this one is also very dangerous because it's a dehydrating agent. So it's pulling the water from the molecular structure of the cellulose and turning it into black carbon. So that's why you're seeing a carbonized version of the paper. I could also try to lift it up and see if it made some holes, but you can see that clearly the paper has been totally destroyed. So that is not something you would want to have on your hands. We'll put it to the side and make sure nobody touches that until we remove it. For the second part, we'll also show the same kind of reaction, which will involve some sucrose instead of paper. I mean, cellulose is a sugar, it's a polysaccharide. This one is sucrose, the stable sugar. We normally put this in our teas and coffees. And we're going to react that with some concentrated sulfuric acid, which we already measured in this beaker here. We'll need to do this very carefully. Now, Andres has poured already some concentrated ammonia in here to absorb any possibly dangerous or unpleasant fumes, and I'll need to put some gloves on to make this happen. This is quite a violent change. It will take a few minutes, so we will continue, but the reaction is really simple. We'll just pour it on top and give it a very, very brief stir, just very, very briefly, like that. Now the ammonia is really getting in my eyes, so that's beautiful. Okay. Oof. Okay, so we can cover this with a bell jar, which is probably somewhere over here. Oh, there it is, yeah, okay. We can cover this to contain any possibly dangerous fumes. But before we cover it, you can just have a quick look at the color. The color is changing because also the sugar is carbonizing, exactly as the paper did before. It's just taking a little bit more time, so we can cover it now and leave it covered. It will produce a little bit of sulfur dioxide, again, other sulfurous fumes that will react with the ammonia and will be completely contained by this bell jar. So we can move it a little bit closer to the side because we will need to move on in the interest of time to the third experiment while this continues. So we'll get rid of the bottle for now. We'll need it again later. Then we have here a protecting mat. Can we fit it a little bit further? Yeah, probably like that. Okay, so we have here one last experiment. You see the sugar nicely carbonizing there. That's turning into black carbon. It's basically the water being taken away from a carbohydrate. So you have a carbohydrate which contains carbon and water, somehow chemically combined. The sugar is being dehydrated. The acid is pulling away the water, leaving behind just the black carbon. We'll be able to see what happens in a few minutes. We should go on preparing the last experiment for this section while this reaction takes place, and I hope you all can see it's a very dark black color. So for the last bit, we will have a reaction which is only started, it's only initiated by the concentrated sulfuric acid. It's not a reagent, it's just a starting something used to start the reaction. And it will be the reaction between potassium chloride and yet again some sugar. This is a quite unstable mixture. It's used, potassium chloride is used in pyrotechnics. It's a very good oxidizing agent. It contains a lot of oxygen chemically bonded. So we'll mix these two things together, creating a rather unstable mixture, which is totally fine at room temperature until we add a drop of sulfuric acid. So probably something like that much should work. And a little bit more icing sugar. This is just finely powdered sugar. The more finely powdered it is, the faster the reaction it will be at the very end. So we'll need about twice as much, more or less like that, yeah? In the meantime, the carbon is forming in the beaker, so I don't know if you can all see the layer of carbon being formed. We have here the two powders, and we'll try to combine them together very, very intimately. It's very wise and much safer to do this on a piece of paper without too much grinding action, because that can set it off unexpectedly and blind us or kill us all. So we'll need to be extremely careful with that. And that is the... Oh, there it is. That's starting now very nicely, so I will pause for a minute with that. The fumes are basically the products of this dehydration, mainly sulfur dioxide and other sulfur-containing fumes, which are now reacting with the ammonia, forming a very dense white smoke. And in the meantime, something else is going on, but probably you cannot see it because of the smoke, so we'll need to wait a few more seconds, and when we think this is over, we can lift it up and see if any surprise has appeared inside this container. So I think the reaction is more or less subsided still a bit more. Yeah? We can leave it for a little bit longer. So in the meantime, we can go back to our little powder here, which should probably be now fairly well mixed. Maybe one more time, just pouring it from one sheet to the other. There you go. And we have now a special container where we can put this in, which is quite a heavily used crucible, this one, where we'll put our mixture ready for the reaction with sulfuric acid that will initiate the change. There it is. So thank you very much. So we'll have that ready here. We'll make a little indentation in the middle for sulfuric acid. And shall we proceed with that first, or we'll move?
Let's have a look under here.
We should have a quick look
first. Yeah. Let's have a look.
So we'll have a quick look.
Let's just push this away a little further. Yes.
Just in case.
So have we got the bags ready?
Okay.
So this reaction should now have finished, and we hope to see the results of sugar having been dramatically dehydrated by concentrated sulfuric acid. What happens when you remove the water from it. We're going to have to put the container fairly soon into a bag, but it's no rush. And there you can see it has risen. You can see it has risen. And Jacob, could you help? We need 2 people to hold the bags. Yeah, that's right. Put that straight into the 2 bin liners. There you see. Can we just hold it up for everyone to see? Dear children, this experiment is frequently by children called the Big Black Monster experiment.
Yeah,
and you can see why. And you can see why. And what we've actually produced in this is a lump of pure carbon. And there's another one from a few days ago. That's what the result looks.
Safer to handle.
It's called sugar carbon in the world of chemistry. And if you can detect a smell, well, that's the smell of burnt sugar primarily. Dear sir, on to the next one.
Yeah, we can finish off this section with the last demonstration, which is the mixture we prepared before, containing, as I said,
watch carefully. There may be a second black monster coming out here.
And also quite a bit of flame.
We have to take care with this one.
So we can have maybe the lights down for this one. It starts, this will produce, of course, a lot of energy because we are mixing a very strongly oxidizing material with a very fairly good reducing agent, which is sugar. So we'll put just a drop of our concentrated sulfuric acid on, and this will activate the reaction. We can have the lights down, please. Thank you very much. There it is, and there it is, a beautiful flame. You can see the violet color of potassium ions and a lot of energy released by the combustion of the... And again, another black monster being formed due to the carbonization, this time due to the heat, not to the acid, of the sugar we started with.
Thank you very much.
So with this, I hope I showed you some activity of sulfuric acid.
So there we are. So there we are. Thank you very much. Thank you very much. Thank you, Fabio. So we've seen 2 black monsters in the last 3 minutes, dear children. I am going to show you now something very interesting, which could also relate to Italy, and I wonder what the connection is. But we're starting off with sulfur once again. One of the amazing things about sulfur, which people have always found from very early times, is the fact that it melts quite easily. I've already shown it to you burning, but I'm going to show you how it melts. By the way, what is happening there is quite important. Andreas has now put a burner under a flask which contains, again, concentrated sulfuric acid. But I hope you can see inside, we put the acid in already. It takes about 5 minutes for the acid actually to start reacting with what you can see inside is actually copper. We've got tiny pieces of copper in there, and the acid will react with the copper to make sulfur dioxide, which is the gas that I explained to you at the beginning. When sulfur burns in oxygen, it makes sulfur dioxide. But concentrated sulfuric acid also makes sulfur dioxide when it reacts with metals. Now, that takes about 5 minutes to heat up. And in the meantime, I am going to show you a very interesting result that can be achieved with sulfur. Sulfur exploiting the fact that sulfur has a low melting point. Now, the fact that sulfur has a low melting point of 115 degrees centigrade has been exploited not only to make what I'm going to hopefully make for you in a few minutes here, but also it's been exploited in making molds of all things. A mold is something where you make a nice shape or an interesting shape. Please watch while I attempt to demonstrate for you something very interesting with sulfur. So I'm going to melt the sulfur. Now, as we heat the sulfur up, it's a solid. You can all see that. But gradually, it will start to melt. It will gradually start to melt, and it turns to an amber liquid, a liquid which the color you see there it is, that's an amber or an orange color, and it's a liquid which is very runny, and you'll see it very shortly. The trick is to keep it heated evenly for a reason which you will very soon observe. Can you see it's a runny liquid in there? Can you see now? It's very, we call that a mobile amber liquid. You could see me shaking up. But now, dear children, watch carefully what happens. And as I start to heat it up to a higher temperature. I'm going to shortly make the sulfur boil, because the hotter the temperature, the more likely it is. There it is, you see. It's very rapidly moving around. But now watch what happens as I start to warm it up to a higher temperature. So you notice the color goes slightly darker. Notice it's still very mobile. Notice it's still, but hang around, it's beginning to change slightly. Is it changing? It's certainly getting darker. The color's getting darker. And is the mobility of it decreasing? Keep watching. Whoa, almost fell out, didn't it? That was a close one. That would have been very embarrassing. Magic, dear children. Look, it's stopped pouring. Has it become a solid? That's the question. Dear children, I can explain this. You see, the sulfur starts off, sulfur has molecules whose formula are S8. It's a very unusual. They're puckered rings. They're like little crowns. And as you heat these molecules up, they start moving around. But when you get to a temperature of roughly 160 degrees centigrade, which is pretty warm, then they suddenly break up. The molecules of S8, they break and they start making a polymer. They polymerize like a plastic, which is what you saw. Now, what I'm going to try and do, it's got hotter now, and it's now beginning to start pouring. Then it's beginning to start being mobile again. I'm going to pour it into some cold water. I'm going to pour it into cold water, dear children. Let's see what happens as I pour it gently into cold water. And there you see, it's forming a liquid which is going in and forming a pattern at the bottom of the beaker. And I'm going to push it down with my copper pipe a little bit to make it go. There we go. And you see it continues to pour in. Beautiful, golden, like golden syrup, dear children. And very shortly, I shall show it to you because I'm going to take it out. There it goes. Push it down into the water. It's sticking a bit. That doesn't matter. But it's pouring continuously, you see. And what I've made in here, dear children, it's what we call plastic sulfur. It's a very unusual kind of a sulfur because it's neither a liquid nor a solid. It's a sort of in-between layer. And there it is, you see. I can now allow that to carry on dripping. Now, Andres, could we quickly get a mat? I just want to put this down somewhere. Just get a mat, please. That'll be very kind of you. And I want to show the children what I've made in there. And I want to show, thank you so much, Edie, that's most kind. I'm just going to put this down here. In the meantime, I am now going to show you, see these beautiful golden strands. I'm going to take them out with my fingers because they're quite cold now. And you see, dear children, what I've made here, it's called plastic sulfur. It's quite stringy. And the reason why it reminds me of Italy is because it looks a bit like spaghetti. So here you see sulfur in the form of almost a spaghetti-like substance, and you'll be most welcome to come and have a feel of this afterwards. It's quite safe, but it's a form, it's as I said, it's called plastic sulfur. After a few days, this will start to solidify. And dear children, because sulfur, don't take the heat away because I've still got to do a couple of experiments, dear sir. I'm going to show the children a few molds. Because sulfur is so suited for pouring, people have thought of making molds with it. And here, Andres has prepared for you a fish which is made out of sulfur, which has been cast in a special way. And here, Andres has also made some little models. I think you will recognize what these, but this is all made of sulfur, would you believe it? But not only that, dear children, sulfur has been used for making. Sulfur has also been used. Are you already collecting? Okay, well, sorry, this experiment has run out of control. Maybe I'll simply turn my attention to this then, Andres. In here there is a rose. Have you actually filled this already? Okay, so that rose is started off with this color, and sulfur dioxide bleaches rose petals. It's been used as a bleach and a fumigant since ancient Egyptian times. It's been very well known that the gas produced by burning sulfur, and so that rose will gradually lose its color. Can we just interrupt this, or shall we carry on with this? Because I've got to show those. But let's just interrupt this for a second, because I do want to show everyone these molds. And what happened is I will show you these molds here. Not only that, the sulfur was also used for making molds for sweets, would you believe it? And in the approximately the ninth, about 1,000 200 years ago, well over 1,000 years ago, about 1,200 years ago, the great Persian doctor and physician and alchemist Al-Raziz, who was the first person who started making marzipan from almonds and from honey. And Al-Raziz introduced marzipan into Europe through the Hanseatic ports, and one of those was Lübeck in the North Germany. And there, today, you can actually see in one of they have a fantastic marzipan cafe there, which sells not only marzipan, chocolates and cakes, but also wonderful coffee. And this is an actual mold made for making marzipan confectionery. It's a sailing ship, and that dates from 1880. So that's the tradition of using marzipan molds, rather using sulfur for molds, has been well known for many, many years. Now, not only is it used for confectionery, but it's been used for making a most remarkable machine, an electric machine, which I wanted to show you here. And the electric machine was first produced by Otto von Guericke, the German scientist and physicist. And could we have the next slide, please? And this special machine is based on the idea that sulfur is known to attract, to have magical attractive forces. Jacob, could you please demonstrate for us? There was and have we got the bits of paper somewhere? We've got these. So Jacob's going to just very quickly show you that if you take a lump of sulfur and you rub it on with a silk cloth, there are some bits of paper here, these tiny little squares of paper. The idea is to try and stand maybe around so the people behind can see. That's right. And just show you a little bit. It's not a brilliant experiment. We haven't got it to work. It depends on the weather as well. But the honest truth is it's got to be bone dry for this experiment to really work well. But if you now, let's just see what happens. And with a bit of luck, it'll start to pick up bits of paper. And there you see it's picking up bits of paper there. Now, those are magic forces, and people used to observe it picking up bits of hair, bits of feather, and those magic forces, people had asked themselves questions. Why does this happen? Why does sulfur do this? Not only sulfur, there was another mineral called amber, which they found on the beaches, and that too had this same property. And this property, a view of sulfur attracting things, was further developed by Otto von Guericke, and he made a special globe out of sulfur. And this picture which you see, that slide there, shows you the real thing, the globe which he made and out of sulfur. And he described the remarkable reactions that he would achieve of things attracting themselves. Now, being attracted to it, should I say. Today we call this electrostatic. It was the birth of electrostatics. And we have an amazing friend of ours who has especially, his name is Markus Bildhammer. He's from Germany, and he heard about the lecture here, and he especially has made a von Guericke electrostatic machine, especially for you for today, dear children. We have this machine here, you see, and we're going to, we know it's not easy to get results, but we will try and get you to charge this up by rubbing my hand against it, and then actually one of you guys, if you would just practice this a little bit, and I'm going to show you how it affects feathers. I'm going to simply suspend some feathers over this. Could you please look, charge it between you, just charge it, yeah, just turn it rapidly, Thank you very much. And now watch me, watch what happens as I bring the feathers. There's a wind coming, I fear, from somewhere. That would be, it should have a very slight effect on the feathers. You see, what it does is it repels them. Can we just try? It's not an easy experiment. And children, afterwards, we can try this again. You can try this yourselves, you see. It's a very difficult experiment because you need very dry air for this to work. Static electricity is a very sensitive. You know, on a hot, dry day, if you touch the handle of a motor car, a spark jumps. Well, we're certainly nowhere near sparks jumping, but you can see the feathers. There is a slight repulsion. Depending on how I turn them, they repel one another. As I said, I can do this. We could practice a little more, but I don't want to spend any more time. But this ball has been made out of sulfur. That's the important thing. And it was cast in a flask. Otto von Guericke described it. It's the size of a baby's head. That's the exact term which he used. In the meantime, Andres has been collecting sulfur dioxide, which is produced from the reaction between copper and sulfuric acid, and that's going to be our next topic. Andres, how many jars have we got?
This is the
now?
last one.
This is the last one, okay. So in here, we have had the reaction between copper and sulfuric acid, and Andres has been collecting gas jars of sulfur dioxide. And I just wanted to show this remarkable gas, which we make so much use of on an everyday basis without knowing even. This gas has some very, very interesting chemical properties. Now, the reason why sulfur dioxide is so interesting, and why indeed the chemistry of sulfur is so interesting, is because sulfur is a very, very reactive element. Not only is it reactive, but it can form many different kinds of chemical combination. And I will just explain a little bit on that in a little bit more, but we will first just finish collecting this last gas. Now, is this last gas, the way we test, by the way, for a gas which is full of sulfur dioxide, is to put in a burning splint. And what we've done here is just put in the splint there, and you see it's gone out. That means that this is now full of sulfur dioxide, and because it's full, and there is still some sulfur dioxide coming out, we are now going to very carefully connect this apparatus to a drying tower. And this is called an absorption tower. This is actually an absorption tower in this case. You see, in here, there is a tower, and that's got soda lime in it, which is an alkaline substance, and it absorbs and it reacts with the sulfur dioxide, which has come off in there. So that means it won't escape into the atmosphere. I mean, we can smell it a bit here. Maybe you can, but as you see, it's nothing too much to talk about. It's just a little mildly irritating, but no harm whatsoever. Dear children, I am now going to show you some experiments with sulfur dioxide, just to show you what a splendidly reactive substance this is. And you've already seen the rose will, as I say, it's definitely being bleached. It'll take a while, and maybe that's all it'll do. But the fact is, you could see it's definitely gone pink from red. And I just wanted to show you a couple of other experiments. Now here, I have another gas which contains sulfur. This gas comes out of volcanoes as well as sulfur dioxide. And this is called hydrogen sulfide. It's the gas which used to be called rotten egg gas. It has a phenomenally unpleasant smell of rotten eggs. Apart from that, it's unbelievably poisonous. So it's something that you have to handle with great respect, but it undergoes an extraordinarily interesting reaction with sulfur dioxide. So here we have sulfur dioxide, here we have hydrogen sulfide. These two frequently come out of volcanoes together. I am going to show you what happens when they come out of volcanoes and when they mix. And the way we do it is simply by removing the two lids here. And this will take a few minutes. There we are. I've removed the two lids, and you can immediately see what's beginning to happen, dear children. You're beginning to see that the lower jar is going yellow. And the reason why it's going yellow is because there is a new substance being made. I very much hope you can all guess what's yellow, dear children. And if you can't by now, then you haven't been listening. Dear children, of course, we have made sulfur here. We have made sulfur. Now, this is one of the most extraordinary reactions that I'm going to turn it upside down. I want to make some more sulfur, dear children. And in addition to making sulfur, this has also made a tiny bit of water. It does actually make water. And I'm not going to take the risk of holding the two jars and allowing, because there is a partial vacuum in there, but I'm not going to allow to take the temptation of letting one hold the other up. But this is a very interesting reaction from many points of view. To start off with, two gases have reacted together to make a solid and a liquid. The liquid, by the way, is water. You can see some droplets of water floating around. So two gases have reacted to make a solid and a liquid. Secondly, two compounds of sulfur have made the element sulfur, which I personally find also amazingly interesting. Furthermore, it's a most interesting example of a redox reaction in which sulfur is reduced in one of them and oxidized in the other. So that, you see, most importantly, and many geologists believe that these two gases come out of volcanoes together, and they make huge deposits of sulfur, which are found at the mouths of volcanoes. Today, for instance, sulfur is still mined in some countries by people, especially in Indonesia, for example. They climb up the volcano side and they carry huge chunks of sulfur down, and that is, actually, it's a very dangerous thing to do, but it's the way that some people have to earn a living. And so today, of course, we don't extract sulfur from volcanoes typically. Sulfur is today obtained mainly from extraction from fossil fuels, from coal, from gas, and from crude oil. We extract the sulfur using various extraordinary chemical processes, and that's our main source of sulfur today. Dear children, let me show you this. This is a jar full of sulfur dioxide. Look what happens when we pour potassium permanganate solution, which is purple. Look to see if you can observe anything happening. And you see it's lost its color. Let's try another one here. This is potassium dichromate solution, dear children. Watch carefully what happens. Magic? No, it's chemistry, dear children. And once again, we have two remarkable examples. This is potassium permanganate, this is potassium dichromate, and in this particular case, the sulfur dioxide is acting as a reducing agent. It has caused them to change color on account of the change in oxidation state of manganese from +7 to +2, chromium from +6 to +3. Now that's A-level chemistry. Don't worry if you don't know that yet, dear children. But I think it's unbelievably interesting. And furthermore, I wanted to do my final experiment with sulfur dioxide now. Thank you so much, sir. And that's to burn a piece of magnesium ribbon. Now, watch carefully. I hope you can all see. Can they all see? I think that they can all see. That'd be easier. Thank you very much, dear Andres. Andres is very much as you could see, my right-hand man. So there's magnesium burning, and now we lower it into sulfur dioxide. And the amazing thing, it carries on burning. Could we put the split on top? It carried on burning for a little while. And what happens is in sulfur dioxide, magnesium actually breaks the bonds between the sulfur and the oxygen to make a little bit, that wasn't actually probably totally full of sulfur dioxide, but you saw the principle. It carried on burning and it splits the oxygen from the sulfur, itself becoming magnesium oxide, which has fallen to the bottom and releasing a little bit of sulfur on the way. So that's an example of sulfur dioxide as an oxidizing agent. Now, as I did mention earlier, sulfur dioxide has many uses, and the use that I personally find is the most important is that it's actually present in many wines. And I've got a bottle of wine here, which actually, some of you might not believe me, but we're going to look at the label with a super camera which we have here, and I wanted to show you that the label actually says sulfur dioxide. So I am shortly, and look very carefully, usually, by the way, sulfur dioxide is used as a food preservative, right? But they usually call it sulfites, which is the sulfite ion, SO3 2-. Are we getting it a little bit further away, maybe, Andres? Yeah, that's it. I think we could see it. Contains sulfur dioxide. Can you see, dear children? Now, isn't that amazing? I will, as soon as this talk is finished, if I get to the end, I'll be drinking a bottle of sulfur dioxide in your honor. So we'll keep this for later, dear children. But hang around. No, we'll do that. Let's do that later because I'm in a hurry. We have lots more chemistry to show you. Dear children, let us now return. We can turn this off. I'm now going to return. And for this very day, this is going to be the most dangerous experiment of the day today. We are going to see what's happened to the copper. You see, I've showed you sulfur dioxide, but what's happened to the copper? Has it become copper sulfate, which many people might think? Now, Andres, very careful. Is this still, okay? Okay, it's okay. We've got to leave it clamped now. No, take the top off, okay. Disconnect that. This has got to be firmly clamped. I am now going to undertake the most dangerous experiment of the day. So please allow me very carefully to move the apparatus around a bit. Because you see, I hope you can all see, by the way, that it's black at the bottom, we can leave that there because, well, we can take it off. I hope you can all see that it's black at the bottom. That's the important thing. That black stuff, where has that come from? It's come from the copper, you see. But what is that copper actually turned into? What sort of substance is it? Does it contain sulfur? Because we started with sulfuric acid. That's what we're going to investigate at the moment, dear children. Now, to do this, I have to access the copper. I'm going to now pour into it some, now where's the, sorry, before I do so, where's the water? Is that water? That's too big a flask. Is this water in here? I'll do that. Sorry, we have to be very careful that we're using the right apparatus, dear children. I'm going to pour into some here, some concentrated ammonia solution. Now, ammonia is a strong alkali, and it has a very powerful smell as well, and it neutralizes, you saw in that bell jar, all those fumes. We're going to make those same fumes here. But when I add this very carefully, you'll hear little explosions inside, and you'll see a huge amount of white smoke coming out. That is because the alkaline ammonia will be neutralizing the acid in a most violent reaction. And as you see, plenty of white smoke, plenty of noise. Now, I have to take great care to do this gently. We're nearly there. We're not nearly there. Dear children, I've added enough ammonia. You can certainly see that's neutralizing the acid, and we're still interested in what's in the bottom. That's the thing, I draw your attention. Having added the ammonia to partly neutralize the acid or all of the acid, I now need to pick this up in my hand. And I will do. I've got special gloves down here somewhere, which I'm going to put on. There. Thank you so much, Andres. I'm going to pour in the water very carefully now. This too will boil. The purpose of adding the water is to cool it down and to dilute it. And I have to do this very carefully. And shortly, when it stops bubbling, that means that we've got to a stage where it's relatively safe to handle, which is now. And now at this stage, dear children, I am going to, you can see it's black. There's a solid in there. There's a mess in there. I want to separate the black solid from the liquid so that you can all see what color the solution is. And in order to do that, dear children, we're going to use a filter paper. We're going to filter it. But I have to now very carefully hold the flask, which is very hot indeed because the water has just boiled. And I'd like you to see what the color is of the liquid which comes through. This is the important thing. So we're now filtering. We're just giving a little swirl around. You see plenty of white smoke, and we're seeing what color the solution comes through. And there you see, dear children, a beautiful blue color. A beautiful blue color. Now, that's all we need. We've got enough for the experiment. Now, that beautiful blue color, dear children, is due to copper sulfate. We've made blue vitriol in here, which is what we'd expect. However, there is a surprise, dear children. There is a surprise. Because what's that black stuff? You see in the filter paper, there is a black residue. Now, what I'm going to do is I'm going to remove the filter paper and place it into this beaker here. I think we can now I tell you what, let's first of all add more water to it to dilute it. We're just diluting this now, by the way. And we're going to put this here. Thank you very much, Andres. That's now, we're going to look at that filter paper in a minute. So just leave it to carry on. And you see this beautiful blue? Children, there is one test which we do for compounds of copper, and that's to add ammonia solution. And if this really is copper, let me add some more water. Let's dilute it, because I want the color to be really faint. Because what you're going to see is hopefully going to be quite surprising and very beautiful indeed. As I add a strong ammonia solution, watch carefully to the color. And there you see the appearance of an intense, deep blue color. You see, oh, it's gone. That's odd. That's very strange. Let's carry on, dear. I thought I had seen it, but obviously I hadn't, so I'm sorry about that. Let's try a bit more then. Look, I'm sure that's blue now. So let's give it a little swirl around. And there you see. Well, I thought I'd seen it, but you know what I've got? I have an intense blue color. Now, dear children, this is the special test that we do for compounds of copper. And the blue color which we have there is called the copper tetramine complex. It's unbelievably sensitive for even the tiniest amounts of copper. And we've managed to demonstrate that supremely efficiently in this excellent demonstration, which Andres, by the way, he did it all by himself, you noticed. Andres, thank you so much. Dear children, though, this is the bit which is really bizarre. I tell you what, let me just take my gloves off. Let me take my gloves off because I don't need gloves for this. I wanted to show you just what's left inside. Dear children, inside there's a black solid in there. It hasn't yet fully, there's still a little bit of filtering going on, but you can see on the side of that. So what is that black solid? Now that's a very tricky one. And I have to tell you that chemistry teachers and chemists for a long time have been intrigued to know what it is. It's copper sulfide. It's a very unusual substance, and it's a certainly unexpected product here. And it just goes to show you how when we do chemical experiments, very frequently there are substances or reactions that are not that obvious, immediately obvious. And copper sulfide is certainly not one of them. And as I read, actually, I discovered there are many copper sulfides. CuS and Cu2S are just two of them, but there are many others, and they are formed depending on the temperature and the concentration and all the rest of it. No, we finished this topic, though, very successfully indeed. And we've shown you not only the sulfur dioxide, but also what has happened to the copper. Now, we're now moving on just a little bit further. Could we have the next slide, please, which should be a periodic table of there. Thank you so much. Dear children, you cannot possibly give a talk about sulfur, the most extraordinary substance known to humanity, without showing it as an element. Now, this is a periodic table of the elements. I know there are some of you who know it off by heart, because I've seen that before, but you look at sulfur, it's element number 16. It's on the top right-hand corner, and it has a symbol S, as you see there, S standing for sulfur. So that is the symbol there, and I just wanted to tell you that sulfur is unbelievably reactive. I think I've demonstrated, but one substance that I haven't spoken to you about today is another kind of a bond. Sulfur can form 4 hooks, 2 hooks, -2. Oxidation states +4, +6, and -2. 0 in the oxidation in the element. But I have here a most interesting substance I wanted to tell you about, and that is sodium thiosulfate solution. Sodium thiosulfate contains the ion S2O32-. Sulfur is on the periodic table. That will stay there to the end. It's very reactive. And in here, I have a solution of sodium thiosulfate. It's got the ion S2O32-, which is quite unusual. And if I now add to this some hydrochloric acid, I'm going to show you a most unusual effect. So I'm adding hydrochloric acid here in a few doses, and I'm going to hold it up for you all to see and swirl it around. Now, this reaction will take, I don't know how long, but can you see it's happening already? Look, can you see it's going cloudy and cloudy and cloudier? What color is that, children? Yellow. It's yellow. Now, if someone said blue, you've got a surprise coming for you. I've got a surprise coming for you, because that was a very good answer. But at the moment, we could see, I think we'll all agree it's yellow. Now, what substance is in there that's yellow? Sulfur. Well done. Oh, I'm so happy that someone's learned something. So that's through. If you'll remember after this talk, the word sulfur, that would be absolutely amazing. So sulfur, there it is. And dear children, in this reaction, we have sulfur, which is produced inside the solution. You can't see through it anymore. And this topic, this specific reaction, was the focus of one of the most interesting experiments that used to be demonstrated by Professor John Tyndall at the Royal Institution, precisely in this room, back in the 1860s. This was 160 years ago. Now, Jacob and Andres will now set up and demonstrate for you this experiment. And dear Andres, are you ready to take over? Thank you very much. So Andres is now going to explain to you what's going on in this reaction here, which has been especially demonstrated by Professor John Tyndall about 160 years ago in this room.
So we're going to do the Tyndall effect. What that consists of is what Andrew was doing here, but on a very slow rate. We're going to make colloidal sulfur, which are very, very tiny particles of sulfur. And in order for this to get it going, I just need to add some dilute acid to the very dilute thiosulfate solution to make those very tiny particles of sulfur. Okay, now you'll notice in a few moments, hopefully, that if we can get the lights down, please, the beam should be clearly visible. Give it a... And also, we should expect to see a color change because those tiny particles of sulfur, the scattering light, especially the blue part of the white light, I add a bit more acid. Not yet.
Is it a beam of white light that you're shining, Andres?
Yes, it's a torch at one corner.
Okay, so what's interesting is that we can see actually the color does appear to be blue, doesn't it? The color appears to be blue, and it's the same reaction that I demonstrated in this flask here, but done to take a little more time. It's to enable the tiny particles of sulfur to grow very, very slowly. And as they do so, they interact with the beam of light. And the tiny particles of sulfur are called colloidal sulfur, and they're too small to be seen by eye, and that's why you can't see. But the light is definitely beginning to show it, and you can see the brilliant effect is now appearing. Can I hand over to you again, Andres? Tell everyone what's happened.
Right, so now if you, I don't know if you can see it, it's turning bluer and bluer, and you can also see more clearly the beam of light. That's the scattering going on due to the very tiny particles of sulfur, which are increasing in amount and also in size at the same time. So hopefully you'll see that you can see a blue light, bluish light, and this is why the sky is blue. We call it Rayleigh scattering. So the particles are the size of about 400 nanometers, which is the length of blue light in the spectrum, color spectrum.
But what's exciting for me, dear Andres, is the fact that it comes out yellow at the other end. I find that absolutely amazing.
So if I turn this over, you'll see that transmitted light, which is the light that goes through, goes orangey red. And this then again explains why sunrises and sunsets are yellow-orange.
Absolutely amazing. So once again, dear children, the use of sulfur to demonstrate something that happens in our atmosphere, which is the scattering of light by tiny dust particles and ice particles high up in the atmosphere. That's why we see a blue sky. Andres, a million thanks for a splendid demonstration. Thank you so much indeed. Now, dear children, we're now moving on back to the sulfides, and could we have the thing? Dear children, metal sulfides, if you just, which one was this? I can't, that was the second one. Metal sulfides are almost all insoluble in water. And this experiment literally takes 30 seconds, but it enables us to prepare for our next experiment, which we're now getting very, very close to the end with. In this bottle here, dear children, I have some sodium sulfide solution. Now that's a soluble sulfide, and what I'm going to do, I'm going to pour in turn, this is copper sulfate, this is tin, this is a copper compound. It doesn't matter whether it's a sulfate. Copper, tin, lead, and antimony. And watch the beautiful colors of the insoluble sulfides as they are formed. So we pour this in, watch the color change as I'm going to pour it in the other way so they could see some blue left over. And there you see, so it goes black there. If we pour now some tin, look at the beautiful color that's produced. And there it is. It's a beautiful orange color. Look now at lead. So this is copper sulfide, tin sulfide. Here we have mercury sulfide or lead sulfide. Yes, I think that's lead sulfide. And finally, we've got antimony, a substance which we don't learn too much about at schools. But let's just have a look, see what this antimony has been known for. Well, there it is. It's gone orange. In fact, it's soluble, but it's got a beautiful orange color. Those are just some examples. I could show you lots more, but we're now moving on to the penultimate experiment, dear children, which concerns a very, very dramatic experiment. And this involves the reaction between metal and sulfur. And the honest truth is this, that metals react very violently with sulfur. And what we're going to do in this experiment, we're going to react zinc with sulfur. Now, that will make zinc sulfide, you will all know. And here I have a mixture of zinc and sulfur. But in this particular experiment, I have mixed them together in such a way that they do far more than just react together. Thank you so much indeed. And have we got... we'll be able to put that on. Dear children, I have to warn you, this is a very violent experiment. Can you see how little powder there is? That's a powder, that's a mixture of 12 grams of zinc with 2 grams of sulfur. When those react together, it's going to be quite an event. And that's why we have to protect you all with this special cage, which Andres is going to put on top. And we're going to now put in a little bit of potassium permanganate, which is a slow, which will give me, actually I don't need these glasses for this at all. I'll tell you why, because I'm not going to be anywhere near this experiment when it's happening. You're going to be closer than I am. And so there we are. I'm just making sure. I have to do this very carefully, by the way. You must appreciate that we have to take great care with these experiments. And the cage, which is a specially designed cage, which I've built for this experiment, will be very carefully placed on this mixture once I've used my delayed action fuse. Now, I'm using a mixture of potassium permanganate and glycerine, which is well known for producing a fire spontaneously with a delayed action. I'm going to spray a few drops of water on it before I... So there we go. Is there water handy? If not, it doesn't need water on it, but it just speeds it up a little bit. So there's my glycerol and just a few drops of water. And then we're going to ask for lights out. So please put the lid on now, sir, very carefully. And watch the reaction now. Lights off, please. Thank you so much indeed. Watch this carefully, children. And that, you see, is the magnificent reaction between zinc and sulfur to make zinc sulfide and a whole amount of sulfur dioxide. So we're going to ask that off. Dear children, I hope I have given you, thank you so much, I hope I have given you enough evidence and enough demonstration today for you to agree with me that sulfur is indeed quite an extraordinary substance. Now, it is quite so extraordinary that one of my very good friends, Jed Dmowski, he was so impressed when I told him about these experiments. He said, can I write you a poem? Can I write a poem for the children? And he has indeed written a poem for you all. He's written a poem which is entitled Ode to Sulfur. And I'm going to ask Stephen to read this poem to you now, because this will summarize what we all think about sulfur.
Ode to Sulfur by Jed Dmowski. In foul 4 fathoms deep, in years now long ago, the alchemists were working where our darkest secrets flow. From hydrothermal vents they drew their inspiration's fire to make their dark discoveries bring light to man's desire. For science is an art of experiments and trial, of utter dedication, of intelligence. And while we take for granted the things we have today, it's science which asks questions to light and lead the way. Now let us shine its light upon an element of fire, sulfur, burning brimstone, lifted from the mire of centuries of ignorance, of elemental need. It's now we have the answers. It's now we can succeed in giving explanations as to how things work, react, and our focus is on sulfur and on many brilliant facts. It's now well known that sulfur creates profit and great wealth. It contributes to economies, to our joys and to our health. But how did all this happen? What is it we must learn? Every generation must study in its turn sulfur. Its atoms are of subtle depths. Its molecules like stitches, which attach themselves to other things and create a world of riches. Not just riches we can see, but those of thought and wonder, from the way we know volcanoes work to lightning and thunder. Stand back and light the fuse now burning in your mind, which urges you to find out more and value what you find. Through sense and observation, we examine what we see, and mankind has done just that throughout all history. The Egyptians used their sulfur to bleach fabrics, paper too, and when we write our stories, we write on what they knew. The Greeks made disinfectants with sulfur, and they staged their tragedies like burning flames which reach out to our age. The Chinese used it cannily for good things and for bad, from fireworks, nice for parties, to explosives, very sad. In medieval times, the doctors recommended it for worms, and people thought they'd try it, but regretted it. It burns. Now, in our most recent times, sulfur touches all our days. From rubber tires to batteries, it reacts in useful ways. Fertilizers, pesticides, in oils and fabrics too. Sulfur bonds with many things and burns a brightly blue. Its melting point is fairly low, 115 degrees. And when its form is acid, it sustains whole industries. We know it is essential to make plants and foods to grow. It purifies petroleum to make the traffic flow. Even in our bodies, it feeds our DNA. And when it's missing from our hair, its thickness falls away. It's found in fish and beans and nuts, in vegetables. Such worth! Sulfur is an element which sustains our life on Earth. Now, let's return to Dr. Andrew and his science and his knowledge. Don't you feel inspired to rush off straight to college to learn about the chemistry of sulfur we adore? Yes, let's all rush back to school, my friends, and study it some more!
Thank you very much indeed. Thank you very much, sir. Can I ask the author, Jed Mahovsky, the author, to come forward? Jed, can you come forward? Just take a bow. This is Jed, the author of the poem. So, Jed, a million thanks again so much that you've been studying. Thank you very much indeed. Dear ladies and gentlemen, we're now moving on. As you heard in the poem, the expression light the fuse. So that's exactly what we're going to do. Dear children, just a couple of points. Well, I forgot to mention one thing which the poem mentioned, and that's rubber is used in vulcanization. Vulcanization is adding tiny amounts of sulfur to rubber to make it much stiffer. This is unvulcanized rubber. This is vulcanized. If not for the process of vulcanization, we'd have no tires today on motor cars or on aeroplanes, on bicycles. We'll have no hoses in cars, and so on and so forth. In fact, the world would be quite different. Vulcanization was invented by Charles Goodyear in 1840, one of the most important uses of sulfur today. Sulfur in gunpowder, that's the final experiment. Dear children, sulfur, you see here, I know which you can all tell, but these are the three ingredients of gunpowder, which were known to the Chinese over about 1,000 years ago. Sulfur, charcoal, and potassium nitrate. Now, they're used in explosives and fireworks, and especially for today's finale, I have made 4 little firecrackers like this. We're going to fire them all simultaneously. All 4 of us will light a firecracker each. Now, at this stage, they do make very loud bangs, dear children. So this will be the very last experiment. And if we're all still standing and sitting, then we'll have considered this to be a success. So you're the weight. If you don't want to hear the bangs, children, you have to put your hands over your ears like this. And if adults want to do it as well, please feel free. We've got ear defenders. We have ear defenders, and we have actually, I'm going to put mine on last because I have to know what to say to everyone. So let me tell you what's going to happen. These are Mark IV banger cages. This is third in my evolution of these cages. And I have made these little firecrackers out of 2 sheets of A4 paper, wrapped in, as you can see, yellow stands for charcoal, black for charcoal, and yellow for sulfur, you see. So this is color-coded, so you actually know what's inside. Isn't that amazing? And there's a little fuse. So we put these inside here. What we're going to do is to have a bit of fuse sticking out like that, you see. We're then going to take a splint each. We're going to light the fuse, and then we're going to stand in a staggered way because sparks will come flying out. And you will also notice these cages, by the way, they're very safe. They're made of steel, and they will protect us, obviously, but some sparks may go flying out. So let's just rehearse where we're going to stand. So if I stand here, Jacob's there, Andres there, and so we're staggered. So your sparks don't, because you see the sparks might fly out and hit people. So I'll stand here. So we've all got Jacob a little bit maybe more forward. They shouldn't fly that far in any case. Right, are we all ready? Now, hang around. Let me now put my ear defenders on. I'm so sorry. I just got to put these on now. Right, there we are. So we'll all take a light now. So everyone's got to take a light. This requires quite a little skill, as you can all see. And we have to keep the light going. At the same time, we have to put okay, let's keep your light going by holding it slightly like this. Very gentle. Is everyone still got a flame? Have we all got a flame? Andres, are we ready? Is everyone okay? Are we ready? Okay. 3, 2, 1, ignition. So there it is, all successful. Ladies and gentlemen and children, stand. Thank you very much. Thank you very, very much indeed. Thank you. Let's stand in a row, take a bow. Thank you so much indeed. Can we have Stephen to the front? Jed, please. Stephen, all the assistants. Thank you very, very much indeed. Thank you very, very much indeed, everyone. Thank you for your kind assistance. Take a bow. 1, 2, 3, bow. Thank you so much indeed. We wish you all the very best. Thank you so much. Thank you so much. Long live sulfur. Very good for everyone. Thank you very much. I hand over.